Hello, welcome to this second lecture session of this video lecture series for the course Database Management Systems. In this session, we will discuss some more important concepts pertaining to database management systems. In this session, we will learn about describing the data that is being stored in a database management system, tree schema architecture for database management system, data independence, and the brief discussion about the queries and transactions, concurrent transactions, structure of a database management system, that is the various modules which become integral part of the database management system software, and the people who work with database management systems. First, we will see what is a data model. It is a collection of high-level data description constructs that hide many low-level details. Database management systems allow a user to define the data to be stored in terms of a data model. And we have two kinds of data models: semantic data models and representation or implementation data models. When we design our databases, first we do with semantic data models, which will give a very high-level idea or description about the data that is being stored in a database. It is more abstract high-level data model, and that makes it easier for a user to come up with a good initial description of data in an enterprise, contain wide variety of constructs that help describe a real-world enterprise data. For example, we do these semantic data models using ER modeling technique, where we try to describe the data that is being captured in a database in terms of entities, its attributes, association between the entities, and other constraints. Second thing is representational or implementation data models. These are database management system specific data models and are built around just few basic constructs. For example, relational data model, object data model, so on and so forth. A database design in terms of a semantic model serves as a useful starting point and is subsequently translated into database design in terms of the data model in database management system support a specific data model. That means when we do our database design, first we do with semantic data modeling, that is we try to describe the data in terms of entities, attributes, relationships, so on and so forth. Then we need to decide upon or choose an implementation data model. For example, you may choose relational data model, or you may choose network data model, you may choose object data model, so on and so forth. And when you narrow down onto a particular database management system, every management DBMS supports a specific data model. For example, if it is a relational data model, the basic constructs used are relations or tables. And if it is object data models, then the objects, we need to capture data in terms of objects, so on and so forth. So that's why first we will design, do with the semantic data modeling, then we need to translate that into DBMS specific data models or the data models that are supported by the specific database management system. Let us have a look at relational data model. The central data description construct in this relational data model is a relation, which can be thought of as a set of records, otherwise which can be seen as a table of rows. And schema means description about something or a plan which describes something. Description of data in terms of a data model is called as a scheme. A relation schema specifies the name of the relation, field and type, etc. For example, if you look here, the relation name is the student. Student is the name of the relation, which contains three fields: SID, name and age. And each field is also associated with its data type or domain. And each row, every row follows the schema of the relation. Okay, that means the relation schema that we have already defined for this, relation or the table, that serves as a template. Whenever we insert data pertaining to a student, the record or the row must satisfy or obey the structure that we have defined here for the student relation. Now, this particular table student relation contains 3 tuples or 3 rows. Each row of this relation is going to reveal facts about some student. So that's why we have captured information for 3 students. This particular set of records is called as an instance of a relation. This I can call it as the set of 3 records or 3 rows or 3 tuples. I can call it as instance of this particular student relation. Schema is different, instance is different. Like a class, the relationship between a class and an object. Class describes the structure of an object, whereas object is really existing, that is in existence. The instance of a class is called as an object. Object is an instance of a class. Similarly, the relation schema serves as the structure, definition or the description of the structure, and then whereas here the actual tuple, set of actual rows or records, I can call it as instance of that particular relation. Here this is an instance of student relation. A schema can be regarded as a template for describing a student. We can specify integrity constraints, which are conditions that need to be satisfied by records in that particular relation. For example, I can specify unique constraint, I can specify primary key constraint, and we can specify foreign key constraint, domain constraint, so on and so forth. And we can enforce, we can specify these constraints on the relation, and we can enforce these constraints on the instances of that particular relation. When we actually enter data into the table, and the actual data or the records that are being inserted, that should satisfy the conditions that have been laid down in the form of constraints, specified in the form of constraints. Now let us have a look at the other kinds of representational models. We have network model, hierarchical model, relational model. Just now we have seen what is it, object data model, object relational data model. And first we need to do semantic data modeling in terms of, we may use UML or you may use ER modeling there to get some high level description or idea about the initial idea about the data that is going to be captured in the database. Then we need to choose or decide upon the implementation data model. There we can either go with this or hierarchical model, relational model, object or object relational. And in this particular course we try to learn the database management system related concepts in terms of relational model. Okay, and prior to relational model, in early 1960s, one important data model has been introduced, that is called as network model. The basic structure is a record, and the relationships are captured between 2 records using links or the pointers. The database can be seen as a arbitrary network of records connected by links. And the IDS, the database management system called as IDS, integrated data store, which was introduced in early 1960s, was introduced by GE, and it is based on network data model. In late 1960s, hierarchical data model was introduced by IBM, and a database management system called as IMS, that is information management system, is based on this hierarchical model. The records containing data are organized as collection of trees. It is more or less same as network model only, but it is not a arbitrary network, rather it is a tree. The records are organized in the form of a tree. Then in early 1970s, IBM introduced a relational data model called as relational data model. Data and relationships are captured as tables and keys. For example, many commercial database management systems, namely Oracle, IBM's DB2, MySQL, Informix, Sybase, MS Access, Ingress, MySQL, and lot of other relational model based database management systems have been introduced. Here the basic storage structure is a record, but the collection of records is organized in the form of tables or otherwise relations. That's why it is called as relational data model. Now let us take the example of capturing data in relational model, network model, and then hierarchical model. First we will see how data can be captured in relational model. Let us take the example of a banking scenario. We need to capture information about customers, and their account details. First we have customer table, customer relation, then we have accounts relation. The customer relation has customer ID, name and account number. Account relation has account number and then balance. There are three customers in customer table, 101, 102 and then 104, and there are three bank accounts, 10, 20 and 30, and the corresponding balances are given in the table. And the business rule says that same customer can have multiple tables, accounts, and same account can be owned by more than one customer, that is joint account. For example, here the customer 101 owns account number 10 and 102 owns account number 10. That means 10 is a joint account between which is owned by 101 and 102. Similarly, 104 has two accounts, 20 and 30. And now if we want to know the information about what is the balance available in particular account for a given customer, what is the balance for a given customer, then how we can know? Here the account number in customer table is a foreign key which is referring to the account number of the accounts table. So there is a link between this and this, that is being, that relationship between this table and then account table is being captured in terms of this particular account number, which is a foreign key which points to this. Now if I want to know what is the balance for the customer 101, then I can join the tuples which are spread across these two tables using this foreign key, and then if I join, what happens? This particular record can be joined with this record, and this can be joined with this, and this can be joined with this, and this can be joined with this, like this. So if I want to know what is the balance available in customer 101 for customer 101, then I can join the tuples. Now I can say that 101 has the balance 9,000. Okay, like that. This is how the data is being captured in relational model. Everything is in terms of relations. Relations contain set of tuples or records, and relations contain the field names and data types. It is basically record based, but the organization of the records is done in terms of relations or tables. Same data if I try to capture in network model, it can be seen like this. Now I have only records, and it can be seen as a network graph where the records become nodes, and the edges, the relationships or the associationship between the records is working like or seen as edges. Now I have three records of type customer 101, Ram, and these three, whatever I have I am showing here, these three are customer related records, and these three are the account related records. Yeah, this is network model, and here there is no foreign key concept here. I have three records here which are pertaining to customers. Here I have three records which pertain to the accounts table. Now 101, record 101, the name is Ram, and he is associated with the accounts record, this one, the 10. 102 associated with again 10. 104 is associated with 20 as well as 30. This is how we capture, that is, this can be seen as a graph. What are the nodes in this graph? The records themselves, they become nodes, but we have different kinds of records. First three records, they are of type customer, and next three records, the structure is different. Okay, and similarly we try to capture the association or the relationship between the records in terms of pointers. This arrow is a pointer. This is pointing from referring to this one from this particular record. This is how we can capture data in network model, data model. Similarly, if I need to capture the same information in terms of hierarchical model, I can do it like this. And as we already seen, the hierarchical model is also almost like network model only, but this is not going to form an arbitrary graph, rather it is going to form a tree. Now here the same data, in the first row here, in the first level I have all customer related records, in the second level I have the accounts related records. As a root I have a dummy record, and from here I have three customers, and this is what this particular record is, a accounts related record, and which is associated with the customer 101. Similarly, this is a accounts record which is related to customer 102. Similarly, 104 customer Mohan has 2 accounts. So that's why this is linked with, or this is associated with 2 accounts records, 20 and 30, and it is almost similar to that of network model. Only thing is, since I am going to capture the information in the form of a tree, it is going to have some amount of redundancy. You can see that here. So where is the redundancy here? The information about the account 10 is available under 101 as well as available under 102. This is necessary because this cannot be a graph. This is not a graph, and I need to capture everything in terms of a tree. So that's why there exists some amount of redundancy in hierarchical model. And same information, that is the information pertaining to customers and then accounts, is now has been captured using 3 different models. The first one is relational data model, where everything is captured in terms of tables, and second one is network data model, where everything is captured in terms of records and association or links between the records, which forms a arbitrary graph, and next everything is captured in terms of records, but these records are organized in the form of a tree. Okay, it is not a graph. So that is the difference. Then we have seen first 3 data models: network, hierarchical, and then relational data model. And then in late 1980s or early 1990s, another important data model has been introduced, that is object data model. Here in this, what we can do is, we can create objects using some object oriented programming, and then we can store them in the database. And storing objects in relational data model is not possible, because the basic principle or philosophy of relational model is, for a given row under any column, the value I am inserting, that must be atomic and simple. And if I try to put an object for any row under a given column, then under any column, what it becomes? It becomes a complex. Object is not a simple or atomic one. Object, it is a complex one, because objects contain attributes or fields, or some objects may contain objects, that is nested objects may be there. So that's why inserting objects for any given row under a column is not possible in relational model, and that's why object data model has been introduced, where we can create objects and then we can store them in database and then retrieve them back using some query languages whenever it is required by the applications. And next, people thought that this is a biggest constraint, because we have popular data model, that is relational data model, and picking up the new and then picking up data model is object data model, and then according to the rules, it is not possible to, according to the philosophy of relational model, it is not possible to insert objects into the database, relational database. Then they thought that it is a serious constraint, limitation. Then they come up with a new data model, that is called as object relational data model, which is going to bridge the gap between relational model and the object data model. It is via media. That means, for example, you can take Oracle version 8i onwards, it supports object relational model. It is based on object relational model. Informix DBMS also supports object relational data model. That means we can define and then create objects, and we can make them as values under any column, under a given column, for any row if required. So that's why these are the important data models. We call them as representational data models or implementation data models. To design a database, as we discussed earlier, first we need to do, we need to design the semantic, we need to do with semantic data modeling, where we are going to describe everything in terms of entities and then relationships. Then we need to choose one among these available representational or implementation data models, and then translate the semantic data model into the data model specific constructs. If I have chosen to go with relational model, the ER modeling should be converted to or translated into relations or tables. If I have chosen to go with object data model, the ER model entities should be translated into objects, so on and so forth. Then let us have a look at database schema. What is a database schema? A description about a database is called as a database schema. And we have 3 schema architecture in database management systems. A database can be described using 3 different levels of abstraction. Description at each level can be defined by some schema, by a schema. For each abstraction, we focus on one of the specific issues such as user views, concepts, storage, etc. Okay, this three schema architecture has become possible through the abstraction mechanism. What is abstraction mechanism? Humans try to understand something using abstraction. That is, they try to describe something using abstraction mechanism. When we use abstraction mechanism, we can describe some entity or something or some object at different levels of abstraction. At each level of abstraction, we focus on certain things, necessary things, and we hide other unnecessary things. Okay, so using this abstraction mechanism, we can describe the database at three levels, at three different levels: external level, conceptual level or logical level, and then physical level. If I am describing a database at physical level, that is the third one, I will be always talking about how data is actually stored on the disk, physical disk. What are the indexes? What is the record structure? What is the file organization? I will be talking about all those things. That is physical level description. And the abstraction, physical level abstraction I will be using, I focus on only physical storage details and I don't reveal or highlight anything else. And next is conceptual level schema, that is logical level or logical level. I try to describe the stored data items of the data model specific to the database management system. In RDBMS, conceptual schema describes all relations that are stored in the database. Arriving at good choice of relations, fields and constraints is known as conceptual database design. Then at external level, it is used to describe the database at external level, that is at the application level, also described in terms of the data model of the DBMS, and this allows data access to be customized at the level of individual users, groups or applications. An external schema has one or more views and relations from the conceptual schema, and this schema design is guided by the end user requirements. Now I have three levels. At each level I can describe the database. In summary, what I can say is I can describe the database at using three levels, different levels of abstraction: external level, conceptual level or logical level, and physical level. If I am describing the database at the conceptual level, that description is called as conceptual schema or logical schema. And here I am going to describe the stored data in terms of the data model specific to the DBMS. If I am doing with RDBMS, I am going to describe the structure using relations. And then at external level, what happens is the whatever data that is available in the database that need not be revealed or exposed to all the end users. A particular end user or the user group may require only a small chunk of the data that is being stored in the database. Then what I do is I define an external schema for the user 1. I can define an external schema for user 2, so on and so forth. For each user, I define the schema such that he will be able to see only a part of the conceptual schema. Only part of the database is available for him for access. That is the requirement, that is the need, or that is the purpose of these external schemas. Then once done with conceptual and then external schemas, I need to decide upon what are the indexes that need to be used to make the data retrieval faster, what are the table clusters, what are the table spaces, and then what is the record structure. All these things can be decided at can be defined at physical level description, and which is given by physical schema. For instance, let us try to understand this external three schema architecture or three levels of abstraction using a simple example that is about a company database. And first let us assume that we have done ER modeling, and it is like this. Yeah. First, we need to go with high level data modeling, that is semantic or conceptual schema, which is going to describe the database in terms of entities and their relationships. Then we need to translate that into implementation specific or implementation conceptual schema or logical schema, and which is going to describe the database in terms of the constructs that are supported by the DBMS specific data model. If we are going with relational model, let us assume that whatever ER modeling that we have done in this semantic conceptual schema or data modeling, we have translated that into relational schema. That is, everything is now in terms of relations or tables like this. This is logical or conceptual implementation conceptual schema. Let us assume that I have employee table which captures information about employees, employee ID, name, age and department number. Then I have department table which has department number, name and location. Then I have employee project, which then I have project table which gives information about projects, project number, project name and location. And then I have employee project, employee ID, P number and then hours. So this is the conceptual schema which gives complete description about the data that is being captured in a database. That is, in this conceptual schema I have or logical schema I have 4 relations. Now let us assume that I have only 3 user groups, user 1, user 2 and user 3, and they need to be exposed or given access to different portions of the database depending on their requirement. Let us assume that at external level user 1 wants only information about the employees and then employee ID and then department location. Okay, so that's why I will take the first table, employee table, as it is into the logical schema or external schema of the user 1, and then I define or write a definition for the view which gives employee ID and then department location. How can I get employee ID and department location? If I can join the tuples that are spread across this employee table and then department table based on this department number which is a foreign key pointing to this, then for each employee ID and then department location can be extracted. I extract that and then put it here, and it is called as a view. A view is always based on the actual relations that are available in the conceptual schema. And if you carefully observe, I am not going to expose all the schemas, all the relations that are available at conceptual level or the logical level to the user 1. User 1 is given only a small chunk of data that is available with the conceptual schema. Then for suppose user 2 at external level wants employee project name, employee ID and project name and then department information. This department table as it is I am taking into the schema of this external schema for the user 2, and then I am extracting employee ID and the project name from table employee project and then project, then creating a view and then giving it or exposing it to the user 2. And then for user 3, let us assume that he requires only employee and then department location. So I am writing a view which can give him that particular or expose that data to this user 3. That's why all the description about all the data items is available at logical level or available in the logical schema. Then only the description that is required by the specific users or the end users, that is available with the external schema. That is, whatever is the data requirements for user 1 that is available captured here, and the data requirements for user 2 are captured here or given here, defined here, and the data requirements for user 3, external user 3, it could be an end user or a application program, whatever it is, or a user group, it is available at external schema 3. And then at the physical level I try to describe the storage level details for the database. That is how I can I have 3 different levels of abstraction, and due to this 3 different levels of abstraction I am able to describe the database at 3 different levels: external level, conceptual level and then physical level. Before doing this, we must do this semantic data modeling. Then we need to translate that into the data model which is specific to the database. Then you will get conceptual schema. Then we need to define or we need to decide upon the physical level schema. Then we need to decide upon the external level schemas which are required by the end users or different groups, user groups or applications. This is the story about 3 schema architecture for database management systems. Any standard database management systems, it provides this 3 schema architecture, okay, and using which we can easily understand the storage level descriptions and conceptual level descriptions, application level requirements and the descriptions of the schemas for application different users at application level, external level can be understood using this 3 schema architecture. It is like this. So, here we have conceptual level, sometimes it is also called as logical level, and the description of the database at the logical level is given by conceptual schema or logical schema. Then based on this conceptual schema we have external schema 1, external schema 2 and then external schema 3. There, and we have physical level schema or internal level description or the internal level schema, which talks about the internal details or the storage level details. Ultimately the data is being stored in the hard disk. Now you take any database system or it has only one conceptual schema and then it has only one physical level schema, but it can have any number of external or application level schemas. External level schemas can be there for a given database, because same database management system or the same database may be accessed by multiple user groups or multiple applications, and depending upon the data requirements of the end users or the applications, we are going to define the external level schemas for the end users. So, that is why we have only one conceptual schema, we have only one physical level schema, and we can have any number of external schemas. One important advantage of this 3 schema architecture is we are going to enjoy data independence. The 3 level architecture, which is result of the 3 level abstraction on database, leads to data independence. We have 3 levels, that means we have 3 boundaries between 2 layers. Okay, 3 levels means we have 3 layers, and if we go back to the previous slide, so here level 1, level 2, level 3, there is a boundary between these 2 layers, there is a boundary between these 2 layers, and according to this data independence, it says that if there is a change at physical level, the conceptual schema need not be changed. That is, the conceptual level schema or description of the database is isolated from the changes or modifications done to the physical level schema. That means you have physical schema having so many relations in your database or tables in your database. Today let us assume that I am storing it on the disk. Tomorrow if I am changing the storage and if I am going to store it on the tape, still my conceptual schema should be valid. That is, it is isolated from the changes that have been done to the physical level schema. And tomorrow I have one index on table 1, tomorrow I may create 2 more indexes on different tables, other tables, still my conceptual schema remains unchanged. So, this independence is called as physical data independence. Whenever you make changes to physical level, that should not affect conceptual level, it is called as physical data independence. Then whenever you make changes to the conceptual level schema, that should not affect your logical level schemas, that is called as external level schemas should not be affected by changes done or made to the conceptual schema. This is called as logical data independence. So, this 3 schema architecture of the database management system facilitates us this data independence. Changes to physical schema will not affect conceptual schema, it is called as physical data independence. Changes to conceptual schema will not affect external schemas, it is called as logical data independence. This is one of the important and very useful advantages of using database management systems, which we have learnt in the previous class, saying that database management systems, they facilitate or they provide data independence. The DBMS stores, that is, we have seen that we are going to describe the database at 3 different levels: physical level, external level, conceptual levels. So, these descriptions we are calling them as schemas, and these descriptions are stored as data dictionaries or system catalogs. Okay, they are stored in system catalog, and whenever it is required, we need to get the DBMS can get information from the system catalog about the descriptions of the database at 3 different levels. Next, one important advantage of database management systems is queries. Now onwards, we try to understand all the concepts related to database management systems in terms of or in the context of relational database management system. Okay. Now let us see what is the advantage of having a querying system. Queries in RDBMS and not just simply storing data in your database will do, and whenever it is required by end users or the application programs, it need to be extracted or retrieved back from the database for the purpose of data processing and manipulation. That is why how efficient is data retrieval mechanism for a given database management system, that matters. The ease with which information can be obtained from retrieved from a database often determines its value to the user. Relational database management systems allow end users to pose rich class of questions in the form of queries. That is, the users of the relational database management system, they can pose queries to the database to extract or to see the data or retrieve the data, and these questions which are posed by end users to the database management system are called as queries. Relational data model has powerful query languages. We have the query languages for relational model can be divided into two categories: formal query languages and then commercial query languages. Under formal query languages for RDBMS, we have relational algebra and then we have relational calculus, and they have strong mathematical background. Okay, they are based on mathematical logic, and then since the relational algebra and calculus are not user friendly, the end users may not be able to work with those query languages, and all database management system RDBMS vendors, commercial database management systems, they come with commercial query languages, that is they support SQL, that is structured query language, which is a commercial query language for relational data model. Okay. And all database management systems which are based on relational data model, they support by default, it is a de facto standard, by default they support SQL standards. Using this SQL query language, the end users, they can pose queries and then extract data at their requirements. Then when we are using database management systems, we also enjoy the transaction management. A transaction is a collection of operations that perform a single logical operation or function in a database application. You take any database application, it consists of some logical functions. Okay, set of each logical functionality, it is nothing but set of operations. So to understand the concepts related to transactions, let us have a small example. Let us take this railway reservation system which contains some operations or functionality, which provides some functionality. First functionality is to view the availability of berths or seats. Second functionality is to view the trains between two stations. The next one is reserve or book tickets, required number of tickets. The next one is the cancelling a given number of tickets. And actually the data about this, that is the available seats, berths or seats is available in the database. Let us assume that that is captured in the database on the hard disk, captured available in the database on the hard disk, and it is represented by the data item A. And we understand that as of now we have 20 seats available. Now let us assume that if somebody wants to book some tickets, he needs to invoke this functionality. First it will take how many seats are required, then that will store it in a local, because this is a logical functionality, it contains some steps or some instructions to provide that functionality. The second instruction is it will store that in local variable of the program, and if the availability number of available seats is greater than or equal to x, then A becomes A minus x, that is I am modifying the available seats in the database and then collect the money from the, that is make payment, accept payments, print the tickets. Otherwise, that means if the available seats is less than the required seats, then print non-availability of the tickets. That should be the functionality or working of this particular logical functionality for reserving or booking tickets. Now let us assume that I have user 1 and then user 2, and then user 1 wants 15 tickets, he will invoke this functionality. So book 15 tickets, x is equals to 15, and availability, that is A is greater than 15, yes. So A is equals to A minus 15, that is now A becomes, now this is not there, and then A becomes only 5, and then let us assume that immediately after that, after this, that is A becomes A minus x then there is a system crash. Before the money is collected from the user and before the tickets are printed and it has already modified the database, now the available seats are only 5 and the tickets are not issued to the user. Then what should happen? Now let us assume that because it is a multi-transaction or multi-user environment, user 2 also starts with his reservation requirement or the reservation application, then he needs 10 tickets. X is equals to 10, and then but if you see whether the number of available seats are greater than or less than this required seats, it is not so, because since the previous execution of that particular reservation or book ticket operation has already modified the available seats to 5, but still the tickets are not issued, and unfortunately the second user is seeing only the wrong information, and unfortunately he is unable to, though actually the seats are available, since the money is not taken, tickets are not given, the number of seats available are 20, but unfortunately because of this wrong execution of this transaction or this operation, what is happening, it is showing it as 5 and the second user is unable to book his tickets. So this is the anomaly, this is an undesirable property of these database applications. So if we now, what we can do is collectively, if we can call these instructions as one single unit of operation or single unit of functionality and then call it as a transaction. Now the basic philosophy of a transaction is all or none. That means once a transaction is started execution, then whenever there is a crash or failure in between, if the transaction is half done, automatically the recovery system of the database will make sure that whatever updates or the changes that have been done to the database by this half done transaction will be nullified or removed. That is called as rolling back. So if you do that, what is going to happen when there is a system crash? Since the transaction is not complete, when the transaction is complete, when it reaches the end point of this particular transaction, a transaction is nothing but collection of instructions or operations that try to access the database data items and then manipulate them. So that's why when it is reaching this point, then only it is end of the transaction, but unfortunately there is a system crash in between. So that's why it is a failed transaction. That's why what the database management system will do is automatically it will remove all the effects that have been done by this half done transaction. So owing to that, what will happen, this 5 will automatically become 20. Now if this second user is starting his transaction, now he will see there are 20 seats available in a particular train and then he requires only 10 seats, he can book his tickets. So this is possible only if you have the notion of transactions, then only it is possible. Okay. Now a transaction is an atomic unit of work that is either completed in its entirety or not done at all. That means you cannot have any transaction which is half done. Okay, the half done transactions, as we have seen in the previous class, they may leave the database system in some inconsistent state. That's why for all half done transactions, whatever are the modifications done, that need to be removed. Then when the transactions are being executed in a concurrent way, and we should be careful and then make sure that the one transaction will not affect the execution of other transaction. That is also taken care by the database management system. And incomplete transactions and system crash, whenever there is a system crash during the execution of a transaction, we need to take care that the effects done by this half done transaction should be removed and then the database system should be taken to previous consistent state and we need to restart the transactions. Then if we look at the structure of the DBMS, it is like this, and this is DBMS, and we have query engine which is responsible for parsing the queries and finding out the execution plans, deciding upon most optimal path or execution plan and executing it. Then we have buffer and disk file manager, which is responsible for managing the space on the RAM. That is, when you want to make some modifications to the data items available in records on disk file, first it should be brought onto the RAM, then only we can do something. So that's why there is a module called as buffer manager which will take care of that, that is managing space and then manages the transfer of blocks between the disk and buffer, that is RAM. Then we have disk manager which manages the space available on the hard disk. Then we have file manager, which manages the files. Okay, that is a table. Suppose a database requires some files, the files are created by this file manager, and the database, the data tables are stored in these files. And then we have recovery manager. Whenever there is a crash, then this recovery manager will come into action and then make sure that the system is recovered from that failure, that is the database system is taken to the previous consistent state. Then we have, because we have the notion of transactions and concurrent transactions, there is some module should be there which will take care of creating and managing transactions. At the same time, when concurrent execution of the transactions is taking place, then we need to be careful about securing or protecting the data from concurrent use by these multiple transactions. When there is a critical data, when one transaction is using that data, it should be protected from the other transactions which are competing for that particular data item. So that is taken care by this concurrency control manager, where we have submodules called transaction manager and then lock manager. And then this whatever is enclosed in this rectangle, that is database management system. Then actual data is stored on the disk. We have index files and system catalog and data blocks are available on the actual hard disk. And these external users, that is web forms or applications, front ends or SQL interface users who are interacting with the database using SQL interface, all of them will be interacting with the database management system, giving their commands in SQL language. So that is why the SQL commands will be given to the database management system. The query engine takes those SQL commands and then it parses and then it generates execution plans, and then it will take help from buffer, disk and file manager to bring the required records onto the RAM for the purpose of manipulation by these end user applications. This is the structure or architecture of the database management. Any standard database management system will contain these modules. And finally, let us have a look at who are the various users of the database management systems. We have data implementers, end users, application programmers, database administrators. Database implementers are those who are actually writing or developing the database management systems themselves, like the programmers or the implementers of the Oracle or Sybase or MySQL, so on and so forth. Then comes end users, who will just use the database for the purpose of storing their data and then retrieving their data for the purpose of manipulation. Then application programmers, and these people, they are the programmers who are capable of writing applications in PHP or Java or C++, whatever it is, okay, for end users, which will contain code that will interact with the databases through some drivers, and then which will manipulate data content in the database or extract data content in the database. Then we have database administrator, shortly we call them as DBA, and whose role is very, very critical when managing databases. And what are the roles? What is the role played by, what are the responsibilities of database administrators? They are responsible for designing of physical and conceptual schemas. That means they will decide the indexes, table spaces, okay, and the relations, number of fields, all these things. Then security and authorization. DBA is responsible for deciding upon what end user group should be given access to what chunk of the data in the database. Then data availability, he will decide upon the data availability, recovery and then backup strategies. Then he is responsible for tuning the database, that is modifying the schemas or creating or inserting or defining new indexes so as to meet the requirements, performance requirements of the end user applications. So the role played by the database administrator is very, very crucial. We have database implementers who actually write the database management system software itself, then end users who just use the database management systems to store and retrieve the data through some application programs. Then we have application programmers who actually write the code to develop application programs which will interact with the database. Then we have database administrators who has whole and sole responsibility of managing the entire database management system. Then in summary, We have seen how data is described in a DBMS using schemas, and what is a data model, which contains high level data constructs to describe the data in the database, and then what is a schema. It is nothing but description of the database, data contained in the database. What is 3 schema architecture? We have 3 levels of abstractions. Using 3 levels of abstraction, we can describe the database at 3 different levels. We have external level, conceptual level, and then physical level. Because of this 3 schema architecture, we enjoy the data independence. The changes made to physical schema should not affect the conceptual schema. It is called as physical data independence. The changes made to logical schema should not affect external schema, that is called as external or logical data independence. Then we have seen that the all database RDBMS comes with beautiful query languages using which end users can interact with the database to extract the data or manipulate the data. Then we have seen transaction management, which is very important notion in RDBMS, or perhaps many database data models, they support this transaction management, okay, using which we can run we can cater to the requirements of multiple applications running simultaneously. Then we have seen the architecture of any standard DBMS, which contains query engine, which contains buffer, disk and file manager, which contains recovery manager, which contains concurrency control manager. Then at the end, we have also seen the people who are working with the DBMS, database management systems, DBMS implementers, then end users, then application programmers, and then DBA. And with this, we have completed our today's discussion. Thank you very much.